This is the first lecture of chapter 16. In this chapter, we will concentrate on substitution reactions, but this time it's at the acyl carbons. What you'll discover is that the acyl carbons are those that are bonded to a oxygen with a double bond. So in this presentation, we will first look at the general mechanism for acyl substitution. Of course, as you know, the mechanisms are important for organic reactions so we can understand and explain how reactions work, and especially if there are unexpected products. Next, we will look at the reactivity of acyl compounds in substitution reactions. We'll also look at the reactions of alkanoyl chlorides. That's a specific acyl compound that we'll examine. And lastly, we'll do a summary of these reactions. Okay, so let's begin. First, let's re-examine acyl substitution or substitution reactions in general. So here is the nucleophile with its unshared pair of electrons. Remember, they're Lewis bases. Here is our electrophile. Remember, electrophile here means electron loving, which means that it's positive or partially positive. Here is our electrophilic carbon because it is bonded to an electronegative oxygen. So this is our electrophile and this is our electrophilic carbon. Then here is L, and L, as we have defined from previous reactions, L is the leaving group. So after it has left, it is a stable conjugate base. Stable. Keyword here is stable. Notice it will leave with its bonding electrons from here. So the substitution reaction is the nucleophile substitutes for L to form a new molecule with a new bond, as you've seen here. Note again, the electrons in this bond are coming from the nucleophile because the leaving group takes its bonding electrons. So that's an overall view of nucleophilic substitutions at acyl carbons. Here are some examples. So here we have a acyl compound. It's called an acid chloride or an alkanoyl chloride. Here's the acyl carbon right here. Here's our nucleophile, 2 molecules. Here is our unshared pair of electrons. We just need 1. After the reaction has occurred, this chlorine will leave with its electrons, and here they are. And of course, we'll have a new bond here to our acyl carbon. Of course, this comes off as HCl because we have a hydrogen here on the nucleophile. Here's another example. Nucleophile, electrophilic carbon right here, leaving group. So after the reaction is done, we will have a bond from the carbon of the acyl group to the nitrogen. Notice these electrons here are coming from the nucleophile. And of course, our leaving group here leaves with one of these hydrogens. So we have made here a new compound. Of course, as you recognize, this is an amide and this is an ester. And an amide. Okay, so let us look at the mechanism. Again, the mechanisms are very important important to explain certain observations. It's a two-step mechanism, two steps in this mechanism. In the first step, the nucleophile with its electrons attacks the carbon of the acyl group because it's partially positive. What is formed here is a tetrahedral intermediate. Notice that it is an sp3 carbon. Over here it is sp2, but in the tetrahedral intermediate it is sp3. And I'm emphasizing that because an sp3 carbon, the bond angles are 109.5. Much more constrained than the bond angles here, which are 120 degrees. This is an intermediate, as we mentioned. So in a second step, the tetrahedral intermediate falls apart to give the product. How does that happen? These electrons here reform the double bond, as you've seen here from that arrow, and the leaving group leaves with its electrons. Notice, with its electrons here to form a new compound, and that's the substitution product. Two steps. First step, the nucleophile attacks the electrophilic carbon to form a tetrahedral intermediate. In the second step, the tetrahedral intermediate falls apart because we're forming here a carbon-oxygen double bond, which is favorable, and the leaving group leaves with its electrons because it is a very stable, typically very stable conjugate base. So let us look here at the reactivity of electrophiles based on the leaving group. So we're concentrating now on the leaving group. So we have acyl compounds here with different leaving groups. Are they different in reactivity? For example, if this were a Cl or an OH, we would one be more reactive than the other. So what that depends on here is the ability of this L to leave and form here the conjugate base. So if this is pretty stable, if the leaving group is pretty stable, remember we have defined stability as the ability to accommodate these electrons. So as you know, the large polarizable atoms can accommodate that negative charge compared to a smaller one. So here's the trend. Halogens, as you can imagine, are the best leaving group, or one of the better leaving groups. And we have here the acetate anion, followed by the alkoxide, getting extremely poor, the amide, extremely poor, and getting to the H-, which does not leave. It's an extremely poor leaving group because, as you can imagine, the H- is a very strong conjugate base. You may recall that the conjugate acid of H- is hydrogen gas, and the pKa of hydrogen gas is around, well, it's greater than 50, which means that this is very, very strong. So it's not a good leaving group. So the leaving groups that we will be concerned with are primarily up here. Let us look at another aspect here. And this is the reactivity of the electrophiles based on size. So we have the same leaving group here. So just imagine this to be chlorine or bromide. And we will change the groups that are bonded to the electrophilic carbon. So here is hydrogen, and here is your tert-butyl group, very crowded tert-butyl, isopropyl. So remember we said that the tetrahedral intermediate is sp3. So if it's sp3, that means that this would be a very crowded tetrahedral intermediate after the nucleophile has attacked here. This would be a less crowded intermediate after the nucleophile has attacked this carbon. So this is now more reactive as an acyl compound towards nucleophilic substitution compared to this compound, which is very crowded and the tetrahedral intermediate is very strained and in fact very unstable. Notice again that we're making the comparison using the same leaving groups. We're just varying the bonds, the groups that are bonded to the acyl carbon. So in summary, the reactivity is the smaller the group that's bonded to the acyl carbon, the more reactive that acyl compound is towards nucleophilic substitution at the acyl carbon. The larger the group that is bonded to the acyl carbon, the less reactive is that acyl compound towards nucleophilic substitution at acyl carbon. Let's look at another aspect here, electronegativity. So here we're using the same leaving group, but bonded to this carbon is a carbon that has 3 fluorine atoms. Of course, as you know, fluorine is the most electronegative atom, so it's pulling electrons away to the fluorine. So as you can imagine, this carbon here is extremely very positive or partially positive. This, let's go all the way over here. This has 3 hydrogens, not electronegative, more electropositive. So this carbon here is not as electropositive as this one. Another way of stating that is that this carbon is more electrophilic than this carbon. Why? Because we have here electronegative groups bonded to the carbon of the acyl group, pulling electrons away from the acyl group, making this carbon here more electrophilic. As you can imagine, these would be in the middle. So again, you should be able to predict the reactivity of acyl groups based on the leaving group, based on the size of groups that are bonded to it, and based on the electronegativity of groups that are bonded to the acyl carbon. So that's the concept. Let's see if we can apply that. Of course, as you know, my approach here for teaching chemistry is to make sure you understand concepts, and equally important is to make sure that you can apply those concepts to solving problems. So here's a potential problem. We have here pairs of acyl group, okay, acyl compounds. They're acyl because they have the carbonyl group here. So consider this compound and this one. Again, do the observation. They both have Cl as the leaving group, so that's common. But now this one has CH3 and this has CF3, more electronegative. So therefore this carbon here is more electrophilic than this carbon here, making this molecule more reactive. Let's look at this one. Acyl group again. This is CF3, CF3, so that's common. Again, as chemists, you need to recognize and observe common features, because if there are too many changes, it's hard to tell what will affect the change. So these groups here are common, or this group is common with that group. The difference here is that Cl and OCH3, leaving group. The leaving groups are different. So the better leaving group would be the more reactive. So the question now is, out of Cl minus and OCH3, which is a better leaving group? You can tell that by looking at the stability of the group after it has left in terms of the negative charge that it has acquired. As you know, Cl minus is a weak conjugate base, and CH3 negative is a very strong conjugate base. So therefore, this is a better or more reactive electrophile compared to this one. Let's look at this one. Here, the Cl and the Cl are common, so the leaving groups here, or the leaving group here, is common. The difference between these two molecules is that this is isopropyl and this is a methyl, so this is larger than this one. So therefore, the tetrahedral intermediate that will form after the nucleophile attacks this carbon to form an sp3 carbon, this would be more strained, less stable than this one, because there is more space to accommodate that sp3 carbon. So therefore, this is more reactive. Here's one, a little tricky, because the leaving group is different, and the group that's bonded to the electrophilic carbon is different for both molecules. So let's see if we can apply that knowledge to at least come up with a possible answer. So here's a poor leaving group, a very poor leaving group, and here's a good leaving group. Here's a small group, which means that the sp3 for the tetrahedral would be stable, and here's a much larger group bonded to the carbon. So since both factors go against the reactivity of this molecule, it is not as reactive as this one. So again, you can't memorize your way through organic chemistry. You have to really make your observations, and you have to really apply the concepts that we have gone through here. Let us continue. So let us look now at reactions. So we'll start our molecules, or the reactivity of the molecules, with the acid chlorides, also known as the alkanoyl chlorides. But the common name is acid chloride. So as chemists, if you mention acid chloride, we'll all understand what you mean. So the nucleophile will vary. So now we'll vary the nucleophile and react different nucleophiles with an acid chloride. As you can imagine, the mechanism is the tetrahedral intermediate, as shown here in the first step, and in the second step this leaves to form the leaving group, and our substitution product is right here. Okay, so let's carry out the reactions, and don't forget, this time we're going to change our nucleophile. So you need to recognize the nucleophiles. So let us start with water. Here's water. Of course, don't forget, a lot of times we do not put it in, but you know they are there. There are two non-bonding pairs of electrons, which means that this is nucleophilic. Here's our leaving group. So therefore, this will bond here, and this will leave, and the product is this. Notice that it's a carboxylic acid. So we have gone from an acid chloride or an ethanoyl chloride reaction with water to form a carboxylic acid, and of course HCl as the inorganic product. So the mechanism, as you can imagine, is the water coming in, forming the tetrahedral intermediate as we have expressed. Notice there are two hydrogens bonded to oxygen. So here are the two hydrogens. This is an intermediate which is protonated. So in the next step, you can imagine it will lose a proton here, and this will be the tetrahedral intermediate that goes on to form the carboxylic acid. So here's an overall reaction. Propanoyl chloride reacting with water gives propanoic acid and HCl. I should mention that acid chlorides are very reactive compounds in the organic chemistry lab. Whenever you open a bottle, you can literally see it fuming, and if you don't have on your mask or operate in a hood, in this case you need to operate in a hood, it will start reacting with the moisture in your nostril, and very irritating because it's so reactive. So let's look at some other reactions here. So as you can imagine, here's methanol. Methanol, of course, as you know, is very similar to water, except that it has an methyl group in place of one of the hydrogens. So here's our nucleophile. It will react with the electrophilic carbon, and this chlorine will leave as a chloride, of course, as HCl, as you can see in the previous mechanism. So we form here a new bond, and that's called an ester. So as you know, you kind of figure out where this is going. You can make different functional groups here. So in synthesis, we can start with any acid chloride, and we can make different molecules with different functional groups. Here's the same acid chloride, ethanoic chloride, this time with an amine, methylamine. Here is our nucleophilic atom with the 2 electrons. Here's our leaving group. So it will leave with those electrons. These will come in and bond here, and this will go. So we have HCl, and now we have made a new bond, and this is called an amide. As you can imagine, that's a secondary amide. If you use the ammonia, you get a primary amide. And of course, if you use a secondary amine, you get a tertiary amide. Here is an interesting one, a salt, ethanoate, sodium ethanoate. So it's a salt of ethanoic acid. So notice again that it is nucleophilic because it's a salt. And the oxygen here is the nucleophilic atom. Here's the electrophilic atom. Here's our leaving group. So here is the ethanoate portion, which was the nucleophile bonding to this carbon. And here is our inorganic product. This, of course, as you will recall, is an anhydride. An anhydride. So you can see we make different functional groups from acid chlorides. So you can tell acid chloride will be a very, very important starting material for the synthesis of various other molecules. So let us see if we can apply this chemistry here. So the question is to provide molecules, organic molecules, wherever there's a question mark. So we need to put a molecule here, but of course we have to carry out the observations and determine which is the nucleophile, determine which is the electrophile, which is the leaving group, before we can come up with the conclusion. In the next slide, I have some observations that I think you should make before you come up with your answers. So for the first reaction, the observation is this is your acid chloride as a reactant. So here's your leaving group. This is the nucleophile. And the product should be an amide because the N will bond to the carbonyl. The reactant here, we don't know what it is, but at least we recognize this to be the nucleophile, and this is the nucleophilic atom oxygen. Here's the product though. It's an ester, which means that this portion here is coming from our nucleophile, so the acid chloride should look more like right here. Let's look at the other two. Same analysis. Here is our product. It's an anhydride, which means that more than likely this function, this part here, is coming from the nucleophile. Here's our nucleophile. It's asking for the electrophile here, which of course more than likely is an acid chloride. The last one, water. This is a nucleophile, as you can see from this pair of electrons, or one of those pair of electrons. The product that was given is a carboxylic acid, which means that this has to be a acid chloride. But bear in mind though, the acid chloride has to look like that. Make sure you get the structures correctly for these predicted reactions. So here comes the answers. So this molecule here again is a good leaving group. React with ammonia to give the amide bond. So this is the product. This is the reactant, acid chloride, leaving group, nucleophilic atom, reacts right here. That leaves to give this as the product that was given. As we said, this is the anhydride. This is the nucleophile. Here's the nucleophile. So therefore this has to be the reactant, the acid chloride. The last one, water, nucleophile, product, carboxylic acid, coming from right here. So this has to be the acid chloride as shown here. So again, make sure you utilize the knowledge that you've gained. Make some good observations because these molecules will be different, and make sure that you come up with a reasonable molecules when asked these type questions. Okay, let's look at another reaction here. This is the reaction with the good old Grignard reagent. I know you remember the Grignard reagent. That's gained notoriety from Victor Grignard. Okay, but the main thing here though is that R is nucleophilic. You may recall that R is your strong base. It's a good reducing agent. Why? Because it has an unshared pair of electrons on the carbon. Looking at this reactant here, here's our leaving group, here's our electrophilic carbon right here. So you can imagine this is the tetrahedral intermediate, and it goes on to form the product, which is a ketone. And of course the inorganic product here. Here's a trick, however. Now here's what you need to look out for, is that this ketone, that's the product, will react with more Grignard reagent because the Grignard reagent is so reactive. So a second mole of Grignard will react with the ketone, as we have seen before, to form the alkoxide salt, and upon hydrolysis will give a tertiary alcohol. Notice that these two groups here are the same because it's coming from here in the first reaction and it's coming from here in the second reaction. So this is a good way to make tertiary alcohols where two of the R groups are the same. You may be wondering, how do I stop it at the ketone? You stop it at the ketone by using a nucleophile that's not as reactive as the Grignard reagent. You may recall that the organocuprates are not as reactive because the element, the copper, is not as electropositive as magnesium, so therefore it's not as reactive. This reagent is also called a Gilman reagent. So this is far less reactive compared to the Grignard reagent, so it will react with this carbonyl, kicking that out and stop. So this is the final product, the ketone, when we use the Gilman reagent or copper lithium. Here's another example. This reagent here, Gilman reagent, leaving group, reacts here, kicks that out, and this is a ketone. Notice that this methyl group is this methyl group right here. So you can synthesize different type molecules putting on different groups here, or different ketones putting on different groups here, depending on the Gilman reagent that you use. You may be wondering, what about the reaction with lithium aluminum hydride? Because the hydride ion is H minus, very reactive, lithium aluminum hydride. So as you can imagine, yes, it will react here to give this and tetrahedral intermediate, and when these electrons come back in, it forms an aldehyde where this H is coming from the lithium aluminum hydride. Again, as you can imagine, it will not stop at the aldehyde state because this is very reactive. So another mole of this lithium aluminum hydride will react with the aldehyde to give a salt. Upon hydrolysis will give a primary alcohol. So notice again, here's the H from this H, and here's the other H from the second reaction. So this is a primary alcohol. So depending on what this dictates based on the acid chloride that's used. So you can see here where we're going with this. You can synthesize just about any primary alcohol if you choose the correct acid chloride. So same question you may be asking. If you wanted to stop at the aldehyde step, how do you do that? Here you use a less reactive reducing agent, and this is lithium aluminum hydride tert butoxide, a very bulky group here, tert butoxide, which reduces the reactivity of the lithium aluminum hydride. So it stops here at the aldehyde by putting on just one hydrogen. So here's another example: acid chloride reacting with lithium aluminum hydride tert butoxide. We stop it right here. So this is one way of making that aldehyde, and of course, as you can imagine, this alkyl group here comes from the acid chloride. So if you change this to an R, to another group, you can make just about any aldehyde using the appropriate reagent. Okay, let us look here at the reaction with an anhydride. So here is the anhydride. This is a good leaving group, as you can imagine. So we have here the tetrahedral intermediate. When these electrons come back in, this leaves, and this is the carboxylate anion. Pretty stable. Why? Because it's resonance stabilized. You can draw another resonance structure to show that the carboxylate anion is pretty stable. Hence, it is a weak conjugate base, hence a good leaving group. So that's very reactive. Let us see here. So as a summary, let us just look at this reaction here. So the question now is, what reactant goes here if reacts with lithium aluminum tert butoxide to give this here? Functional group here is, this is an aldehyde. This hydrogen is coming from the reactant. So therefore this has to be a acid chloride. This is an acid chloride reacting with lithium aluminum hydride. We'll assume that it's in excess because it has 4 moles of H minus. Here's a leaving group. So what is the product? You can expect that to be a primary alcohol. Here's a Gilman reagent. So it's much less of a reducing agent compared to the Grignard. Notice the R group here. This is the R group right here. So it's a little different from the one we did before. And here we have the product. So obviously, as you can expect here, this may in fact be the acid chloride, because this is coming from that group. And here's magnesium. So we have an excess here of this CH3. Here's the acid chloride, so you can expect that to go, and 2 moles of that to add, because we have an excess to give the product. Let's see what the answer is. So, as you can expect, this is the acid chloride, and 1 mole of H minus will reduce that to the aldehyde. Lithium aluminum hydride. Here is our leaving group, so therefore H minus will react with that electrophilic carbon. So here it is, not shown because we're using the line angle structure. So those are the 2 hydrogens. Here is the acid chloride, or here's a product, and here is our acid, the Gilman reagent, and we're reacting this. By the way, this looks like it's wrong. It should be CH3 to CuLi, because this is it right here. So I'll make that correction when I post the PowerPoints. And the last one here is acid chloride reacting with 2 moles of methyl. So here we have this leaving, and we have, here's 1 mole, and looks as if another one is missing. CH3 and CH3 to form a tertiary alcohol. Sorry about that. I'll make that correction before posting this online. Okay, so with that said, let us just do a quick summary for what we've done here. So the acid chloride, as you can see, it's a very important starting material, because we can use it to make esters by reacting it with alcohols. We can use it to make aldehydes by reacting it with the appropriate reducing agents such as lithium aluminum hydride tert butoxide. We can use it to make tertiary alcohols by reacting it with the Grignard reagent in excess. Here are the 2 groups that are coming from the Grignard reagent. We can make ketones by using the Gilman reagent. We can make carboxylic acids by using water. We can make primary alcohols by using lithium aluminum hydride, 2 moles, or 2 moles of H minus from this, because it has 4, and in a second step hydrolysis. We can make amides by using ammonia and different type amines. So of course, if you use ammonia, you get your primary amide. If you use a primary amine, you get your secondary amide, and a secondary amine, you get your tertiary amide. And lastly, you can make anhydrides by reacting your acid chloride with a carboxylic acid or the salt of a carboxylic acid, the carboxylate salt, to get anhydrides. So you can imagine what's going to be on the synthesis question is, starting with this, show how to make any one of these type functional group. I think this is our last slide. Yes, it is. So continue studying this. I will follow up with another video and do a quick review of this material and move into some more reactivities. But continue studying hard. And again, as we close, remember that as scientists, we are here to devise creative solutions for problems. That's what scientists do. And we are actually using the tools that we've gained from organic chemistry to provide these creative solutions in general for different problems. So keep studying, because this is a path towards becoming a better scientist. Okay?